This time we're given the Ka for niacin, which is pretty much what we calculated in the last problem, and we're asked to find the pH of a 0.010 molar solution and the percent dissociation. This is sort of the same problem that we just did, but in reverse. This time we're given Ka and asked to find pH. Last time we were given pH and asked to find Ka. And notice that there is one significant change here, though. The molarity of the initial HA has dropped from 0.02 down to 0.01. All right, let's give this a shot. We have HA in equilibrium with H plus A minus. So we'll have our initial, our change, and our equilibria. HA initial is 0.01, X initially is 0, and A minus initially is 0. So this has to go in the forward direction. Right now Q would be equal to 0. That's smaller than K, so it goes in the forward direction. So the change for HA will be minus X, for H plus it'll be plus X, and for A minus it will be plus X. So at equilibrium for HA, we will have 0.01 minus X, X, and X. Our Ka expression will be H plus times A minus, all divided by HA. I'm going to plug in some numbers here. For Ka, I'm going to plug in 1.5 times 10 to the minus 5. For H plus and A minus, I'm going to plug in X, so I get X squared, and then down there in the denominator, I'm going to have 0.01 minus X. Okay, now here's where we're going to make an assumption that saves us from having to do the quadratic formula. We saw in the previous problem how when we took the initial concentration and we subtracted X from it, by the time you round with sig-fig rules, it rounds to be the same thing as the initial concentration. Well, we're going to make that assumption here. We're going to assume that X is much, much smaller than 0.01, and that's going to mean that 0.01 minus X is just about equal to 0.01. And oh, the math simplifies a lot. So what this tells us is that 1.5 times 10 to the negative 5 is equal to X squared divided by 0.01, since 0.01 minus X is basically 0.01. To solve for X squared, let's see, since I'm running out of room, I'm going to resume this over on the far left side down here at the bottom. If I take 0.01 times 1.5 times 10 to the minus 5 to clear out the denominator, I'm going to end up with 1.5 times 10 to the minus 7 is equal to X squared. If I take the square root of both sides of that, so 1.5 e negative 7, and then taking the square root, I get that X is equal to, let me move that to scientific notation, that's going to be 3.9 times 10 to the negative 4. Okay. We found X. That's great. The problem is we're not done. We still haven't answered the question, even though we know what X is now. The question asks us to find pH, and the question asks us to find percent dissociation. So I'm going all the way back up to the top to find pH. pH will be minus the log of H plus, and for this we need that equilibrium value. The equilibrium value of H plus is X, which is 3.9 times 10 to the minus 5. I'm sorry, minus 4. So we'll have minus the log of 3.9 times 10 to the negative 4. And if I take the log and I change the sign on that, I get a pH of 3.41. For the percent dissociation, I'm going to get X, which is 3.9 times 10 to the negative 4, all divided by 0.01 times 100. So 3.9 EE negative 4 divided by 0.01 and times 100 gives me a percent dissociation of 3.9. Again, that 3.9% is less than 5, so it's perfectly valid to use the assumption that X is small compared to the initial concentration of HA. Whoops, let me go ahead and mark, because this is a lot of writing on this slide. Let's mark our final answers, our percent dissociation, and our pH. I realize in looking back here at this slide, my exponent right there, my pen kind of dragged. That exponent is a -4, not a -9. And it just wouldn't be equilibrium if we didn't bring in Le Chatelier's principle. So let's take a look at one more example problem here. What we're trying to look at is the relationship between the percent dissociation and the molarity of the acid to begin with. So the question says, compare the percent dissociations we just calculated for 0.02 molar niacin and 0.010 molar niacin. And then see if we can explain the trend in terms of Le Chatelier's principle. Okay, so let's first pull up what our numbers are. So first we'll look at our molarities, and then we'll look at what the percent dissociations were that we found for those solutions. So we had 2 molarities. The first problem we worked with had 0.02 molar, and the second problem had 0.01 molar. For the 0.02 molar solution, we found a 2.8% dissociation, and for the more dilute solution at 0.01 molar, we found a 3.9% dissociation. So here's the deal. Think back to Le Chatelier's principle. We talked about how if you changed the volume of a container, the equilibrium would shift to the side that had more or fewer particles. So if you increase the volume, it would shift to the side that had more particles to fill up that volume. If you decreased the volume, it would shift to the side that had fewer particles because there wasn't enough elbow room for all of them. Well, think about this. Our equilibrium currently is HA in equilibrium with H plus A minus. In this case, we are essentially changing the volume by performing a dilution. If we take a 0.02 molar solution and dilute it to a 0.01 molar solution, as we dilute it, we're adding more solvent, which increases the volume of the solution. So as we go from diluting this 0.02 molar solution, adds solvent. Whoops, there should be another D in there. That adds solvent. And as we add more of the solvent, that increases the volume of the solution. And by Le Chatelier's principle, if we increase the volume of the solution, the equilibrium will shift to the side that has more particles. So the equilibrium shifts to the side with more particles. So that means the equilibrium will shift to the right-hand side, which means more stuff ionizes. So the more dilute solution will have the greater percent ionization. So more dilute means greater percent dissociation. One last word here about weak acid equilibria. Some of the weak acids that we'll encounter are what we call polyprotic acids. Protic refers to protons, and poly means many. So a polyprotic acid is one that gives us many protons. You'll sometimes see the term diprotic for something that gives you 2 protons, such as the example here, H2SO3. That would be considered a diprotic acid. A triprotic acid would be something like phosphoric acid, but whether it's diprotic, triprotic, or has even more protons than that, for any of those scenarios, we can use the term polyprotic. So polyprotic refers to any acid that gives us more than 1 proton. Now, the thing that I wanted to point out here is that if you look at Ka1, which means the equilibrium constant for removing the first proton from this acid, versus Ka2, the equilibrium constant for removing that second proton, there's a big difference, right? There's a difference of 1,000,000 in terms of the size of these two Kas. Removing the second proton has a Ka that's 1,000,000 times smaller than removing the first proton. So what that basically means is that as you start to remove more than 1 proton from a polyprotic acid, it gets to be harder and harder and harder to remove those.